Good morning, good afternoon, and good evening. I'm Tom Concolino, and I'm here with our presenters, Angela Criswell and Aya Takase.
Hi, everyone.
Thank you for attending Rigaku's workshop series on X-ray computed tomography for materials and life science. This workshop will be the first in our deep dive series covering filtration analysis, and will cover CT data collection specifically. This session will be taking place in the lab, with Angela and I reviewing in real time how to develop a scan for filtration media. They'll offer their thoughts on dealing with unique challenges of performing CT experiments on filtration samples. Now, please note, if you missed any of the previous webinars, you can view them on the Rigaku website. We also want to welcome Dr. Philip Eichheimer as a guest panelist.
Hello, good evening.
He'll be able to add additional thoughts and answer questions throughout the session as well. But before we start, a few housekeeping items. As far as today goes, this is going to be an interactive session. So we'll still be taking your questions live during the workshop, and we'll be answering them during the session. So please don't wait until the end to ask. And as usual, please submit those questions via the Q&A button at the bottom of your screen. Now, I won't be monitoring the raised hand function, and I will be posting relevant links in the chat window. Now, we'll be trying to answer as many questions as we can during the workshop, and then we'll respond to any unanswered questions directly after the session is complete. If for whatever reason you have difficulty viewing the workshop live, please note that it is being recorded, and you'll be able to view the recording beginning tomorrow. And with that said, I'll turn it over to Angela and Aya.
Thanks, Tom and Aya, and thanks everyone for joining us for this workshop. And I want to give special thanks to you, Philip. He joins us from Math to Market, and Philip has great knowledge in the field of filtration and porous media, and we appreciate him joining us today to share his expertise. So just as Tom mentioned, we're presenting live from our office in the Woodlands, Texas, and we're starting a workshop series that's focusing on filtration analyses. So before we get that started, though, I'm curious to know where each of you are coming from and as far as this webinar approaches. We'll hand it over to Aya.
Okay, so I'm gonna launch the first polling question. So what brought you here today? You got 4 choices. Number 1, I'm new to digital filtration analysis and curious to see what I can do. Number 2, I'm familiar with the digital filtration analysis, but want to learn more about it. Or you might say, I'm here because I'm looking to purchase some filters or something else. The answers are coming in fast. It's not surprising that the first 2 choices are popular. I'm curious to see what people have in mind when they say other. I'm gonna wait a few more seconds. I think most of you answered it. I'm gonna end the poll and share the results. So seems like most of them are either new to this or familiar to this technique, about a half and half, and 17% of the audience said other.
Well, great. Thanks, Aya. Well, hopefully there's a little bit of some things in here for each of you. And specifically, just to let you know what we're going to cover in this series, we're going to cover CT data collection. We're also going to cover segmentation and property analyses in our filtration analysis. And then we'll wrap up in the 3rd session doing some filtration simulations. But today we're focusing on CT data collection. And in particular, this specific workshop is going to focus on, first, we'll introduce some basics of filtration, and we'll look at how to collect high quality CT data for filter media. And then we'll look at some tips to evaluate your image quality and suitability for further fiber analysis. And we'll be using live in this workshop Rigaku's Nano 3DX system to collect that data. And also you'll see a little bit of the Geodict software package near the end of this workshop. This package is from Math to Market, And for the rest of the series, we'll use it much more extensively. So the first thing we want to do to get started is to cover some real basics about filtration. And before we do that, we're going to go back to Aya, and she has another question for each of you.
Okay, so this is a question I guess Angela is going to answer in a second, but let me ask you first. So what is filtration? Is it particle separation based on flow velocity and the particle volume, or a process in which solid particles in the fluid are removed using a filter medium, or filtrate isolation by an electrochemical gradient? So which one is the correct definition of filtration? So answers are coming in. About half of you answered. I'm gonna wait a few more seconds. I think this one has a very clear winner. Okay. I'm gonna close the poll in 3, 2, 1. Okay, let me share the results. So most people think filtration, I can't say it right, filtration is a process in which solid particles in a fluid are removed using a filter medium.
All right. So I stopped sharing that. And then it turns out that according to Encyclopedia Britannica, that's exactly what filtration is. But you also have to have a fluid that's permitted to flow through, but you have to keep the solids. And the basic requirements for that process is, first, you have to have a filter medium optimized for the size of those particles. Second, you need some sort of fluid with suspended contaminants that you want to capture. And those contaminants may be the things you want or the ones you're going to get rid of. You also have to have a mechanical device, the filter holder, that's going to hold this filter medium in place as fluid flows across. And then lastly, you have to have a driving force to cause that fluid to flow. And sometimes that's just gravity. And in other cases, you may need to apply some pressure to cause the fluid to flow. And it turns out that there's hardly any human activity, whether industrial or commercial, domestic, that's not affected by filtration processes. So it's widely used from your kitchen counter, your Brita type water filter, for example, to enormous wastewater treatment plants, or in the oil and gas industry to provide products to humans. It's also used in the medical field. And just to give you an idea of the size, the global market for air filter media alone was estimated to be $3.8 billion in 2021. So that should convey to you the huge economic importance of filtration industries for both human health, hygiene, and many other applications. So of course, it would be of interest to many in manufacturing and commercial industries to study filtration. One of the difficulties in studying filtration is that we have to address the problem at potentially several different length scales. For example, are we designing a complete working filter? Or are we looking at more basic components? So here I've taken some pictures of an example fuel filter where here's the complete filter. And if we were studying this, we would be looking in the millimeter to meter scale to study this particular complete filter with all of its components. Alternatively, if we're just concerned with the medium itself in this pleated portion of the filter, then we would be dealing in the millimeter scale. And if it's, instead we were really wanted to consider the filter media itself at its most basic, then we're looking at the micron scale. And in some cases, these filter media can even extend into the nanometer size range. And this is actually data collected for this particular media. And you can see these are small circular hollow fibers here that are pretty tightly packed. And that makes this pleated filter pretty firm. So it turns out that the Geodict software can analyze and simulate filtration at all of these scales and even bigger scales. So they can simulate airflow, for example, in a room if you're looking to analyze that. But in this workshop series, we have to narrow our focus. We can't examine all of these and cover it very well. So what we're going to do is we're going to focus on this scale, on the filter media scale, and basically in the scale of microns. Now, these filter media can be composed of many different things. So for example, they can be made from natural or synthetic fibers. They can be metallic meshes. They can be granular media, ceramics perhaps. And again, we can't cover all of those, so we have to narrow our focus. And in this case, we're going to be looking at fiber media. And in particular, we'll be collecting data for a synthetic fiber media from an air filter. All right. So going on, let's just start by considering the problem of air filtration because we're looking at air filter. And so in this case, our fluid is air, and then we have some particulates in the air, some contaminants that we want to remove. And this figure is from Sutherland's Filters and Filtration Handbook, and it shows there's a wide size range for each of these particulates. So let's say we're designing a filter that's optimized to remove atmospheric dust. Then our filter should be efficient to capture particulates in the range from submicron to tens of microns in particle size. And alternatively, if we're designing a filter in a working environment where there's cement dust, then we want to filter this out, and they're in the range of say 2 to 100 microns. So in essence, the starting of the process to design our filters or perfect them for a given environment is that we have to know exactly what we're trying to remove or collect from the air fluid. And if we are a filter manufacturer, it turns out there are some things we may already know about these filter media. So what kinds of things might we already know? Well, we should know the particle size range for what we're trying to capture. That's obviously a given. We should know what kind of fluid we're dealing with. Are we dealing with air, or water, or fuel, or oil, or something else? We may also have already manufactured a prototype or have a sample from another research lab or a company. And it's likely that we know some characteristics of that filter in particular, or may have done some preliminary tests on the media to see its applicability for what we want to apply it to. So things that we might know by doing that process is we should know grammage. So that's the mass per unit area of the fiber media. We'll also know something about the fibers themselves. For example, we'll know the diameter of those. We may know the length, average length of those. We may know the shape of those, whether they're hollow. Are they circular? Are they trilobular or some other type? We will also know if there's binder material in, and we'll know a rough percentage of where that binder material, the number is. And we might know something about how well it captures the particles we're interested in. So those are some types of things that we should know. So you might ask, why do we even want to do this at all? Well, it's much more efficient to model the behavior of filters rather than try to manufacture one that has all types of different solid volume percentages or thicknesses and so on. If we could do that computationally and then select a few to test, then that's much faster and it turns out much cheaper. So you'll see a similar slide if you go to the Geodict Math to Market page. This is really the process of optimizing filtration. So we're going to start in the upper left-hand corner with CT data, and we're going to segment those data and do some analyses on the fibers of an existing filter media. What we can do at that point is we can model, we can change, say, I want to look at different solid volume percentages, I want to look at different fiber diameters, and I want to look at different media thicknesses. So here is just a simple 9 different tests that we can quickly do without making a real filter, put those models through some filtration simulations. And if we were a manufacturer, we might pick a few, cherry pick a few to go through the manufacturing process and test, and perhaps go back again if those don't look like we expect them to, or if we want to perfect even further. So that's generally the process. And of course, we're going to cover the top bar and the bottom right. We're not going to manufacture or test these, but know that that's part of the process. So one of the things that we know from this CT data scale is that we're looking at things that are sized in the micron range. So that means that we're going to have to collect high resolution data. If you've been in any of our workshops or webinars, you'll see we look at things in broad scales. Well, these particular fibers we want to look at are microns in scale. So in order to achieve data collection for that, we're going to need high resolution, magnification, and those types of things. So how exactly are we going to do that? What should we consider? And I'm going to answer that, but first, I is going to ask you a question.
Okay, so let me start the third question. So what imaging conditions should we consider for CT data collection for filter media? So there are multiple choices. One is X-ray energy, or voxel size, or signal to noise ratio, or field of view, or maybe it's all of the above. So answers are coming in. Half of you roughly already answered it. I'm gonna wait a few more seconds. So now I think most of you picked your choice. So I'm gonna end the poll and share the results. So the majority of the audience says it's all of the above. And some of you picked either X-ray energy, signal to noise ratio, or just field of view.
Okay,
Okay.
so it turns out that all of those are very important, and we're going to mention those today. And we're going to start with the instrument itself and ask, well, why did we choose that one? So I mentioned we're going to use the Nano 3DX system by Rigaku. And we chose this instrument because it uses parallel beam geometry. And that's well suited for high resolution CT data collection. And it has voxel sizes in the range of, say, 325 up to a couple of microns. And also we chose this because parallel beam geometry is less susceptible to blurring compared to cone beam geometry. We also use it because it produces characteristic radiation of a given X-ray energy. And so that's something that we'll want to use, and specifically some of the softer X-ray energies. So let's just look at that system. So in this particular X-ray system, we have a high-powered rotating anode. Here's the rotating anode, and it's spinning at very high speed. It has a 70 micron focal spot size where the filament is boiling off electrons and they're focused on the target material. Here we see there's a cup of copper with a band of molybdenum. And so we have a 70 micron focal spot size here. The electrons are scattered off and they will eventually go down through our system. And in the Nano 3DX, we generally can use up to 2 different materials on a single target cup that's easy to switch. So in doing some preliminary experiments, just preparing for this, I considered which one I should use. And I'm going to use an example from some of our older webinars to illustrate how you might choose this. So if you know what your filter media is composed of, then you can choose which particular energy you might start with. So for example, we have chromium that is 5.4 keV, copper at 8 keV, and moly at 17 keV. And what we know is that softer materials will absorb lower energies X-rays better. And the harder the material gets, the higher energy X-rays are more suited. And if we look at an example of a very soft material, in this case styrofoam, and where it's collected at 3 different energies, the chromium, the copper, and the moly, what we see is that trend I was talking about. So as the energy decreases, the absorption and contrast are going to improve. And because this is a soft material, it doesn't really absorb those moly X-rays as well or efficiently as it does for the lower energies. And in our case, I told you earlier, we're looking at an air filter with synthetic fibers, and it turns out copper's well suited. So we're going to be using copper 8 keV energy. Now, what happens after the sample? So remember, in addition to optimizing contrast and energy, we're going to need magnification of the filter media, and so that we can resolve these fibers. How is that achieved with this parallel beam geometry? Well, recall that cone beam uses mechanical magnification. In the case of this particular system, we're going to have to use a lens. So what happens is that after the beam passes through the sample, X-ray photons hit a scintillator, and that converts the X-ray photons into visible light. And then you can use this optical lens to magnify the image before it is captured on the detector. And our detector in this case is a fast CMOS detector. And to change the magnification for our experiment, we have to physically change the lens. But how do we choose? Well, remember, we know something about our fiber media potentially, so we know the size range we need to look, so we could perhaps choose the right lens. So let's say, for example, our fibers are tens of microns on average, then 5x magnification will be just fine. And if our fibers are on the order of, say, only a couple of microns in size, then we're going to need higher magnification, and we might switch to a 20x lens, which, as I mentioned earlier, has a 325 micron voxel resolution. And the next question, of course, you're going to ask is, well, is that process hard? And it turns out it's not. It just takes a few seconds. So you physically remove the lens, put the next one on, and then you run a automated calibration procedure. It takes 6 minutes, and then you're ready to collect data. Now, another thing you'll notice, and of course you'll respect if you've watched our past workshops and webinars, is that as you change the magnification, you get larger voxel size as well as larger field of view. So we're going to have a 2.6 millimeter field of view for our synthetic air media fibers and 1.3 unbent voxel resolution. So that's not where we stop, right? We need to consider other things in addition to just the X-ray energy and lens that we need to use. But we're almost ready to collect some data. So let's talk about these other data collection settings that are going to affect our contrast and ability to resolve filter media. And those are going to include things like bin mode as well as exposure time. So first, let's look quickly at binning. When we bin, our 1x1 voxel can be doubled to a 2x2 voxel or made even bigger. And we want to ask the question, what's going to happen when we bin our images? And before I answer that question, we're going to go back to Aya for another question.
So I'm going to launch the last question of the day. So choose the correct statement or statements below. You have 4 choices. 1, decrease the voxel size helps to resolve fibers in CT data. Number 2, sample movement is rarely a problem with collecting data for filter medium. 3, signal to noise can be increased by increasing voxel size. And number 4, decrease the voxel size increases errors in fiber diameter measurements.
That's a mouthful. Those are kind of wordy, aren't they? Sorry about that, guys.
I thought it would take a little while to think about them, but answers are coming in pretty fast.
Yeah.
We're about a half.
I guess we have
45%.
experienced CT tomographers here.
Uh-huh. Is it tomographer a word?
I just made it up if it isn't. Hopefully that is a word.
I like it. It's about 70%. I'm going to give you a few more seconds. Those might take a little longer to interpret. Okay, so I'm going to end the poll in 3, 2, 1 and share the results. So it's pretty split, but I think the first one was the most popular. Decrease the voxel size, help us to resolve fibers in CT data. Is there any wrong answers to choose, Angela?
There are. So it turns out the favorite answer here, the most selected, is absolutely correct. The second in the list, that sample movement is rarely a problem, that's incorrect. As we get to higher and higher magnification, even small movements can have just very dramatic effects and result in very blurry data. So that's false. And one of the other things that is true is signal to noise. It's increased as you increase the voxel size. And the bottom one is incorrect. So as you decrease the voxel size, you increase the resolving power. So it'll decrease the errors in a sense. So that's the answer to this question. It's kind
There
of
you have it.
mixed bag, isn't it?
Gonna
Okay.
Stop sharing. Okay.
So first thing, let's just look at that in a couple of examples. So here we have some data that is collected with different binning modes for a synthetic filter media. In 1x1 bin mode, the voxel resolution is 1.3 microns. If we 2x2 bin is 2.6, 3x3 is 3.8, and so on with 4x4 and 5x5. And in this view, we're looking at the same single fiber from each data set. And we want to ask, what is the effect of the voxel size in terms of our eventual analysis that we're going to do? Well, if we could just back of the envelope, we could just estimate the fiber size here. We could assume they're spherical. They look spherical. We could fit a circle and look at the X and Y and multiply that times our voxel size, and that'll give us a size for this particular fiber. And in that case, the 1x1 binned image says this fiber is 16.6 microns, and it eventually gets larger, and it's almost 31 microns for the 5x5 binned. Now, what we really ultimately want to do is not estimate size for every single fiber. We want to do this and calculate an average. And that's just exactly where Geodict comes in and is quite powerful. And if we ask Geodict to look at all the fibers in this whole CT data set, then it says, okay, the 1x1 is on average 17.7 microns. It increases a little bit and it's even worse. So I picked a smallish size fiber. And in fact, it's closer to 40 microns average fiber size. One of the other consequences of the binning is that our porosity is going to change as well. So as the fiber size increases and binning increases, there's also a decrease in the calculated porosity. And that's because as the fibers get larger, then more of the mass is associated with the fiber rather than air. So if we were to plot these values across a number of different data sets, we would see something like the following. As voxel size increases, fiber diameter is going to increase and the porosity is going to decrease. And based on this, we can come up with some general rules of thumb of what our voxel size should be based on our known fiber diameters. And ideally, it should be about 1/5 or smaller than your average fiber diameter. So each of your fibers should be covered by at least 5 voxels or more if you want to be able to calculate their diameters correctly. So now let's zoom out and look at a broader view of this same media and ask about, okay, so we talked about estimating fiber size. How about our resolving power for these fibers? And in this case, we'll consider a couple of fibers that are close together in in the bottom half of these little selected 2D cross sections. And one way we can do that is we can simply draw a line across those fibers, and we can look at an intensity profile rather. And what we especially want to consider is whether or not the fibers are resolved. So what we would ideally want to see is the intensity between the fibers return to background. And in fact, if we do that, and we look in this region, we see that for 1.3 micron or 2x2, 2.6 micron, and 3.8, we can resolve these as two distinct fibers. However, when we get to larger bin modes, then these look like a single fiber. And we're actually going to calculate a diameter for that it's a single fiber. And that's why these are biased towards larger fiber diameters on the range of 40 instead of something that's more correct from, say, 16 or 17. So clearly, the smaller bin modes are better in this case. So that means we're going to have to collect longer, but we're going to get better resolving power. One of the ways, of course, we're going to increase the signal to noise is, how about we just address the exposure times? So let's just look at that. And here, this is a different sample. This is a surgical mask filter medium, and data are collected at 15 minutes, 60 minutes, 120 minutes, and 300 minutes. And if we just select a couple of fibers, like we did before, we can look at their intensity profiles for them. And so as the exposure time increases, the signal to noise is going to get better, and we can start to see two fibers again looking for the return to background intensity. So here we would expect in this small white area, the background intensity to be closer to the baseline. And in fact, for the longest exposure time, that's true as we would expect. For the 120 minutes, yeah, probably, maybe for the 60, but the data for 15 minutes is just has too much noise that you probably should consider collecting longer. And if we look at why that's the case, we can dive into it deeper, then we can exactly rationalize that. So let's say that we're going to segment these and we use simple Otsu binarization, meaning we're going to pick a single threshold where we can segment each of these. It's not possible until we get to the higher exposure times. And for these, there may even be some noisy pixels that are chosen, but Otsu binarization is the simplest way to segment. And if you can do it with this, then you're on the way to success. And the reason that it's actually better is because if you look at a histogram of the pixel intensities, you'll see that the fiber in the background overlap for all of these except for the largest exposure time. And that's why you can pick a single threshold to perform Otsu binarization. All right, so if we want to resolve these fibers, we're going to have to collect long enough. Now, once we have segmented our fibers, what sort of analyses can we do with Geodict? So some of the things we can look at are porosity. We can look at the fiber diameter, of course, the fiber's orientation. We can model those fibers and then go on to perhaps some simulations where we look at pressure drop, pore size distribution, pass through the filter media, and then eventually look at its overall efficiency. And those are the things that we're going to do in the second and third workshop series. Okay, so now we're ready to move on to our interactive portion. Maybe as I get situated, you could, if there are any questions, now might be a good time.
All right, so we did have a few questions come in, Angela. The first one is, and I think you showed this earlier in the session. It passed me by as I was trying to get some of the links copied into the chat group there. What's the lower voxel limit for the Nano 3DX? What's the smallest voxel size we can choose?
325 nanometers or 0.325 microns.
Okay.
So we can see something. Remember, we need multiple voxels, so we can see something that's several voxels in length. So about a micron.
Okay.
All
And
right.
then we've got a couple of questions here that were related to kind of your last couple of slides. You had mentioned, kind of how you pick peaks with the different voxels. So is there a threshold or a best practice to saying that your binning is too large? right? So is it like a peak to weld, a peak differential? Is there any good rule of thumb for that?
So let's
Or-
go back to that. Hopefully you see the slides. And let's just go back to,
I think it was slide 28, Angela.
yeah, this one.
That one.
Okay, here. So in this case, we're looking at an intensity profile for a single line, but in a sense, you could see where you could easily select a threshold. Even this line, if you selected it here, you would be able to isolate most of the fiber versus the background. Here, you might be more hard pressed. You'd have to pick something lower and you'd see that you pick up some of the background pixels and mislabel them as fiber. Here, it would become even harder. And here, it's just way too noisy. So for these two lower exposure times, picking a threshold of some value is going to be difficult. And that's illustrated absolutely if you look at all the pixel intensities in that Otsu binarization. This is just looking at it at a smaller scale.
Okay. And then one more question. This is actually based on, I believe it's slide 30, where you talked about improving longer data with signal to noise, right? So the question is it faster to use machine learning, deep learning versus just collecting longer data to improve segmentation? Is that, are they catching up? Is the computer catching up to the actual data time?
Yep. So I think the path you take first is, can I use the simplest thresholding to segment? And the next step you might take is, can I do some image filtering or noise reduction to reduce it so that I get a clear delineation between peak and background? So that would be the next step. And then you move on to deep learning and machine learning, because you recall that in order to do machine learning and deep learning, you have to give it a trained data set, and the human's doing that. And there's ultimately the error that we bring into the experiment because we mislabel things as well. But that might be the path you go. And it turns out that Geodict has all of these capabilities, so you can try them out on your own. You can use noise reduction, you can use machine learning, for example.
Okay, all right. I know we have a couple things going to still, so I'm going to hold on to a
Okay.
couple of these questions. We'll ask them during a couple other spots.
Okay, so let's switch over quickly. Gotta switch the share, new share. Gonna go to here, and you should now see an instrument interface.
We
You
do.
see that? Excellent.
Yes.
So the first thing I need to do is I need to put a sample inside the instrument. And to do that, I have to unlock the door. So there are safety mechanisms that I can't just willy-nilly go up and open the door. And we're going to look at that. So now what's happened is this door open button is activated and I can physically open the door and we
We're
can have a look
still-
inside.
Angela, we're still
Right.
looking at the control
Oh.
software.
Yep, switch your camera
New
view.
share. I selected the individual application rather than
Oh,
the
and
screen.
not the whole screen.
Yes,
Oh,
now
there
I've
it
got
is.
the whole screen. So hopefully you should see it now.
Mhm.
Very good.
So you can see the flashing door open button. As soon as I click that button, that comes on and we can see inside. And here upstream is where our rotating anode is. And we can place any filters that we need for our particular energy or experiment. And downstream of that is where the sample will go. And you'll see it's very close to the face of this lens where we would switch it out for different magnifications. So it's simply unlocking this thumb screw, pulling it off, putting another one on. And so this is going to produce the magnification and the image is going to get collected on the detector. And our particular sample for today is going to be this air filter media, just a synthetic fiber. And I'm trying to find a good background where you could see this. So I've just simply cut a piece, small piece out of an air filter that you would use in your home. I have the same one in my home. I'm sure my husband's not real happy with me cutting those up, but I did. So it's all in the name of science, honey. So I'm just gonna move this over a tad so I can get in here, and I'm just gonna tighten this thumb screw for the sample. I'm gonna look at the instrument because I can see, is it even in the field of view? Of course, I have some movement that I can adjust, but this helps me get it close, right? All right, that's actually pretty good. So then I'm going to close the door in this case. You won't see that. And in here, I'm going to lock the door. So the first thing we need to do here is to center the sample. And to do that, I'll open the shutter by clicking on Start Live Image, and I can pick on a location, right click, and it'll translate that selected point to the center of the image. And of course, I want to do this in a couple of different orientations. So I can change this and say, let's rotate by 90 degrees. And look at it again. And I'm just looking to make sure we cover the filter. I can also look at the visible image up top. It's not perfectly centered, but it sure is good enough. I'm just gonna move it over a tiny hair. All right, so once it's centered, I can just have a look back at 0 to make sure everything's, I didn't do anything to move it out of the way, but it was so close to center that it shouldn't have a problem at all. And then I'll stop the live image. So then we're ready to collect some data. And to do that, I'm just going to use a continuous scan here on the right side. And what we'll see is it gives me some options for up top binning. We're going to do this quickly. We're going to choose 4 by 4. And it says, okay, for that 400 should be sufficient. I'm going to collect for 2 minutes. And it just need a name for this, and I'm going to tell it to run. All right, so in just a second, we'll see it update just below this radiograph view. It's going to tell us how much time is left before it completes the data collection. And we have a little bit more time here. We have 2 minutes,
Okay.
if you will.
So we've had a few more questions come in. I'm going to put the first one here from Mohammed is what if we increase both X-ray resolution and time? So it affects the visualization of the following results. And it says, what time is considered an ideal time for, sub-micron processing? Is there a, again, kind of rule of thumbs, or is there a, can you address that? It's kind of a broad question.
Yep, it is, but that it's a good question. And I can give you some answer based on the preliminary experiments I did with this, as well as just surgical masks. So this is made out of some synthetic polymer type material. I'm collecting it really fast, and it turns out we're going to get great signal to noise in 4 by 4 binning. If, however, I want to decrease the voxel size, like you're saying, then I'm going to have to extend the exposure time. And in this case, I'm going to need an hour or more, ideally a couple of hours, to get to the contrast level that I can use something like Otsu binarization. Now that's for this sample. Let's consider that surgical mask that I showed you some data for. In that case, these are probably cotton fibers, and they are even less absorbing than the synthetic fibers. And in that case, we're going to have to increase the exposure time even more to be able to get good contrast for those. I don't know if you noticed it, but in the surgical mask, there's also thinner fibers. So it's a layered product that has thick fibers, thin fibers, and thick fibers. It's actually those thin fibers that are doing the filtration for you. And those might be the ones that you do your simulations on. So you want to look in that area to ask, am I not only resolving large fibers, am I also resolving the small fibers and getting good signal to noise for those? So in general, when using this instrument, your data collection in unbin mode is going to be from anywhere from 2 hours to 20 hours. Usually I end up in the range of 4 to 8 for good contrast for small samples that are lightweight materials.
Okay. So we got a couple seconds here. We've got one more question I think we can squeeze in. And that's what are other factors that affect image contrast, and can they be tweaked for better contrast?
Yeah, well, depending on your sample, if you're looking at living things or no longer living, but dead, say bugs and things like that, You can use stains to enhance contrast. So that's one thing you can do. You can use things like phase contrast, and there are some reconstruction tools and hardware that accomplishes that for you. The other thing you need to consider is the centering. Remember, things move. When that happens, you get blurring and reduction of signal to noise. So we're going to look at centering right now. If I open this reconstruction window. And here what we see is a radiograph on the left. And for this single line here, we've done a quick reconstruction using this center value. And if I go in a given direction, what we'll see is that these fibers get out of focus. So what we need to do is to use the correct center value that aligns the source, the rotation, and the detector center. So we can just quickly go through a few of those. And there are some auto centering tools that we can use as well. And it turns out for this particular magnification, we just need to use a center value of 0. Once we're done with that, we can click the CT reconstruction. That takes us several minutes. So what I've done is like a cooking show. I've already got that ready for you. So Julia
We can now
Childs.
call Angela Martha.
Martha.
Martha Stewart.
Wow, I wish I could do half the things that she make half the things she makes.
I'm pretty sure that she has many assistants.
Oh, I'm sure she does. I'm sure she does. Just close this. And the next step here is we want to go to our Geodict software. So I've opened that here, and we're going to go through the process of looking at doing some initial calculations to ask what's the fiber size, what's our solid mass volume, and so on, and how does that compare to what we know or expect for this given filter material. So first thing I need to do is to choose a project folder, and I just have this deep dive folder that I've already made beforehand, which I'm going to use. And then secondly, I have to import those data that I just collected. So when I select that in the bottom left-hand portion of the screen, you'll see it's updated import GeoVol. So I can browse to where my data are. And we collected the 4x4 bend. It has a 5.1 micron voxel size, and say open. I just need to select one of these, and this window opens here. So it tells us how big this image is. If I can crop it at this point, but really all I need to do is to give it the correct voxel size here and click on image processing. And the next thing it's going to do is it's going to open some windows that offer us tools to process the images or segment and label those images. And we're going to start here with image processing. And one of the first things we want to do is to perhaps crop this so that we're only looking at the filter media itself rather than considering a broad range of air. And I know some good values here. Let's see, 180, 320 works. 100 and 420. And how about make it just a little smaller, 380. Now we have this single box. And so I could navigate through this filter and see fibers. So I'm going through the plane in this horizontal direction, and I can also look along the vertical direction as well. I'm happy with that. Then I can just click apply, and it'll quickly crop it for me. And then I can, wow, the controls are in my way. I can zoom a little bit. Here we go. Zoom in a little bit more on those fibers and see that I've got them all here. Okay. All right. So now that we've done that, the next thing we want to do is to segment them. And I talked a lot about OTSU binarization. So that's under image segmentation, global thresholding, and you'll see these simple methods with the OTSU here. I also mentioned that there are other types of segmenting that you can do, and those are shown down here as well. You could use them. So we could effectively paint different voxels and ask it to learn from that teaching data set and to segment based on that. But we're just going to use OTSU in this case. And if we look at that, we see in red the threshold that separates fiber from background. And if we just check that at a couple of places, it looks pretty good. If we go to another section and look at it some more, that looks pretty good. If we are not happy with this, then what we can do is we can choose manual under the method and we can move this threshold value ourselves. One thing I didn't mention is in the bottom right here, we see the histogram of pixel intensities. I'm going to select this as a decent segmentation, and I'm going to select it. One of the other things that I forgot to show you here, but as you select a given threshold value, you'll see that it gives you the calculated solid volume fraction for those voxels labeled in red. And choosing this segmentation, we should have a volume fraction of 0.926, et cetera. We also know that for this given Otsu binarization segmented image, that our grammage is 99.2. And we should have an estimate of what's correct or what's not. And it turns out this is on the higher side. So like I said, our porosity or solid volume fraction is 0.926. So if we wanted to do this for a few of these, we might have some spreadsheet here, 9.3, that we keep track of them. We'll say close. We will close this dialog. We can have a look at how well this did. So for example, this is a 2D cross section. I can look at it in 3D. So here it is. It's showing the CT scan. We can filter that a little better so that we don't see the background intensities here. What's it doing here? There we go. I can turn off the segmented portion and we see the filter media itself. And we can zoom in and have a look, and we can manipulate some of the visual characteristics of this to get a great image. We can also look at that portion that's selected as fiber versus background, and we see that here. Kind of hard to look at, so there's some settings in the camera that allow you to see things a bit clearly. And basically what you want to see is clean segmentation, and you don't want to see background pixels or voxels that are labeled as fiber because they're not, right? So then what we want to do is, if we're happy with this, we want to estimate what or calculate what those fiber sizes are. We'll go to Analyze Fiber Find. And now in the bottom left-hand corner, we see Estimate Fiber Diameters. We're going to go through this in much more detail when we're looking at property analyses. So just suffice to say, for now, we're going to only analyze the diameter for those solid materials of fibers, and we're going to move the segments at the background or edges of this box, and we're quickly going to run. So now we get some estimation of the fibers, and what we see is the average size is 23 with a standard deviation of 6. So I could enter those values, do the same for several other different size voxels, and also look at the grammage to see if it is approximating the correct values for what I need. If we want some more detail about these fiber diameters, you'll see here's a histogram that you can plot, but it's already done that for us. So we can look at a plot of the fiber diameter. It's in meters by default. That's the default unit for Geodict. But if we don't like that, then we can certainly change it to something else quite easily and apply. So now we have our fiber diameters plotted in microns and their volume fraction. And you see that just above 20, that's our biggest one. And it's a single peak. So we have only really a distribution of fibers of a single diameter in that case. So that pretty much sums up what you would do. We would recollect in a different bend mode or a different exposure time, for example, and look at a table and compare all of these to see if we're ready and happy with the results to do further analysis. All right. So with that, I think it's time to go back to our presentation here. Hopefully you see that now. Do you see the slide again? Okay. And I'm just going to sum up things real quickly. So the things that we looked at in this particular workshop is we had to look at some filtration basics and describe why we do this experiment in the first place. We looked at how to collect high quality CT data for specifically filter media in this case. And we did some evaluation of the image quality and calculated some parameters to test the suitability of our images for fiber analysis. And with that, we'll wrap up and have time for Q&A, I guess.
Okay. Thank you, Angela and Aya. We do have time for a short Q&A. At the moment, we've just got a single question in, and I'm hoping that I'm phrasing it correctly for Philip to be able to answer it. So the question is there a difference between, and this is in Geodict, between, say, air particles or particles that are in a gaseous medium versus aerosols, which are in a liquid medium? So does Geodict handle those differently, or is it the same?
So by definition, I would just say that aerosols are a mixture of solid or fluid particles in the air. And I would refer the air particles to be like particles of the air. So like, for example, molecules. In Geodict, we can both model these kind of structures. We can set all the parameters in the particle size distribution. So here, for example, would then use some kind of measurement on the particles and then give directly the particle size distribution into FilterDict to simulate the filtration on the filter media.
Okay, perfect. So good to know Geodict is able to do all that functionality. So that is in fact all the questions that we do have. So
There's another one.
Oh, did we get another one? Did it
Yeah.
just come in? Okay, here we go. Is there a good thickness for filter samples? That's probably broad, but
That's a good
Angela, you
question.
may have some thoughts on that, or Philip, you may have
Yeah.
seen from experience as well.
Well, I'll answer it for the air filter, and then Philip can give a broader, maybe more accurate answer. But let's say if we consider the air filter alone, we're trying to catch particulates, but we don't want to make it so thick or so fiber dense that the air can't get through it. So have you ever been in your house and all of a sudden you hear thwack when the air comes on? Well, it's probably because your air filter's clogged or not suited for proper airflow. So the right thickness will depend upon what you're trying to measure or what you're trying to capture. And the right solid volume fraction is also equally important for what you're trying to capture. And I'm sure it's different whether it's fuel or air or water or whatever. Any thoughts on that, Philip?
Yeah, so I think most of the answer has been also given by you. I think it strongly depends on the application and the purpose the filter is serving. Mostly like when, for example, if you make it too large, sure, the pressure drop will be very high, and this is like not something you would accomplish in the air filtration application. But for example, we can have a lot of structural features, for example, to change the orientation or something in this kind of feature where you can improve the pressure drop or the filtration efficiencies.
Gotcha. Very good.
Okay.
Yeah.
So Walter asked a follow-up question because I didn't understand his question initially. Is there a good thickness to test on this instrument? So I think that comes down to how big of a sample can we use with different with different magnifications, with different resolutions.
Right. So for the 5X lens that we're using, our field of view is 2.6 millimeters. And ideally, we don't want a lot of samples sticking out of the field of view because it's also absorbing. And it's you want it to be approximate to the size of the field of view, really no more than a couple times the field of view. Like I said, you don't want it sticking out. So ideally, something that's between 2.8 and say 3.4 to 3.5 is perfectly suited for this magnification. If we were on the 20X, where you have half a millimeter, then of course you want about a millimeter or less to not have so much of the sample sticking out of the field of view.
Okay. All right. Thanks, Walter. Hopefully we got you on the second try. And so that's all the time we have for questions. And again, there are no additional questions, so we can move on to the next slide, Angela.
Yes,
All right.
absolutely.
So as I said earlier, a recording of the webinar will be available tomorrow, and an email will go out to all registrants with instructions on how to view the recorded presentation. So links to the resources mentioned today will also be shared on the landing page. We'll be hosting another interactive workshop focusing on filter media segmentation and property analysis on Wednesday, November 16th at 2 p.m. Eastern, 11 a.m. Pacific. The link is in the chat, and we look forward to seeing all of you then. Thank you for joining us, and we'll talk again in November. Bye
Bye.
now.
Thanks for coming.
Bye.
Thank you again, Philip.
Thank you.
Thanks, Philip.
Thank you.